We have come to the final lecture in the course, where now I'm summarizing all that we know in our new tensor notation. And so here, as you remember, is the field tensor. So it's a 4x4 tensor that that now combines the electric field and the magnetic field into one single entity. It obeys the laws of special relativity, and along with it is the companion tensor, the dual tensor, where now we are point of view of the magnetic field in row 1, column 1, and the electric field are in the off diagonal elements. We can now write the current density in terms of a 4-vector, where the time component is the charge density and the spatial components are the currents. We can write the potential as a 4-vector, where the time component is the electric potential and the spatial components are the vector potential. And then now what I've shown before is that you can write down Maxwell's equations and in terms of the fields. So I can now write the derivative, basically the divergence of the field tensor, is mu0 j mu. This gives you Maxwell's first and third equations. Maxwell's first and fourth equations. It gives you Gauss's law. And it gives you the Ampere-Maxwell equation. And if I look at the dual tensor, set that equal to 0, that one gives me Maxwell's second equation and Faraday's law. If you work through all of the various combinations of indices. Now, we could also write the field tensor in terms of the potentials, where I would write this as not the divergence, but as just derivatives, like so. And so the final step in our analysis is writing down Maxwell's equations in terms of the potentials. And so to do that, I could write them now as basically combining this, where I would write the derivative now, or basically divergence of our terms, is equal to mu0 times the current density. Now with these derivatives, the order of operation doesn't necessarily matter, so I could rearrange this and have them as d mu times the divergence of the field minus, now the dot product is between the derivatives, like so. I could write this out in, I prefer this form because you can actually see which ones are, which operators are the dot product between. But you could write it as this. Since this first derivative has a raised index, that means it has a lowered index. And in this case, it would be 2 raised indices minus like so, operating on that. So that's what that would look like. And so if you were to write this out now in terms of dot products and curls, what this would look like is this one would be the gradient of the divergence of A, so that's this first term, minus the dot product of the two del's is equal to mu 0 j. That's what you would get. And so that dot product of the two del's I could write as the Laplacian. So I would rewrite this as the Laplacian of the vector, like so. Okay. So if you remember now, what we did was, in order to clean up this second order differential equation, we applied a gauge. So if we add in something like, we could add, well, if you want to write the gauge in terms of tensor notation, we could write it down that A mu goes to A mu prime, which is just A mu plus our gauge. And in this case, it would be a lower index because it's in the denominator, and everything else in the equation is a raised index. Okay, so this right here, if you applied this, then F mu nu is unchanged. It wouldn't change if you were to add that derivative term to it. Because if you remember our discussion on gauges, that wouldn't have affected it. So the gauge that we found very useful was the Lorentz gauge. Where we said the divergence of A was equal to minus 1 over c squared, the time derivative of V. Written relativistically, what would that look like? Well, I would get this, where this would then, if you remember, I could write this as that right there, which now, now I can write this as the divergence of the 4 vector right here. Or if you want to write it the other way, like so. So this is the Lorentz gauge in tensor notation, which is pretty compact. If we applied that to Maxwell's equations, what we would end up with is the D'Alembertian, which is, if you remember writing it before, it was essentially something like this. But that square term doesn't really look like a tensor, so instead we should probably rewrite it. And so what it is it already has the time and the spatial derivatives built into it. And so in the end, what it is just a dot product of these two derivatives, just like the Laplacian. So I would write it as delta nu, like so, which, written down as Laplacian minus 1 over c squared, derivative of time squared, or del squared minus d squared over d ct quantity squared. So in the end, what you would have is the tensor way to write, or the index way to write this equation after we've applied the Lorentz gauge to it, is this. So now this is the inhomogeneous second-order differential equation that you would have to solve in order to get the potentials. Once you found the potentials, then you could take the derivative and find the field tensor. Once you had the field tensor, you now had the fields, and you could apply Maxwell's equations to the fields and solve almost any problem that you want to. So that ends our discussion of electrodynamics, where we've now studied the electrostatic cases, the magnetostatic cases, the time-dependent cases. We formulated all Maxwell's equations, which have both a spatial and a time-changing part to them. We found the oscillating electric and magnetic fields produced light and radiation. We studied cases of that radiation on insulators and conductors. And finally, we've rewritten Maxwell's equations and electrodynamics in a form that is natural to special relativity.